So let's go ahead and get started with this then, right? Our 21-2 lecture. This is the last lecture before exam one, right? Last material that we're going to cover before that, our first exam, really. And it covers what we call Carnot engines, right? So the T is silent in that pronunciation. But Carnot engines are essentially, well, let's step back a minute. Let's think about what we looked at last time. We started talking about engines. Right? Heat engines specifically, and a little bit into refrigerators as well, but like refrigerators are just reversed engines. So a lot of what we were talking about when we were discussing this was that, okay, well, thermodynamics was really built to describe heat engines, and we have taken all of these steps, building up all of this information, and it's kind of finally all coming together to talk about heat engines. We're using all those details that we've seen from before and really just summing it all up together into one big topic. So, when we were talking about it, we came up with two really important equations, right? We said, okay, well, the inputs of a heat engine should equal the outputs of a heat engine, right? That's energy conservation right there. That needs to be there. But then also we have this equation that describes efficiency, and I think this one is kind of intuitive to say, okay, how much useful stuff do you get out versus how much you had to put in? And we said right at the very beginning, we can't get above 1. No way, right? Above 1 suggests that energy conservation is violated. If workout was higher than QH, it just doesn't make any sense, right? So at most, we can have 100% efficiency if we had a truly perfect heat engine. But I'm here to tell you today that we're not going to hit 100% either. Right? The limit's actually a little bit lower than that. And you probably already kind of know that, but we're going to really talk about why. So before we get into that, though, I would like to look over the laws of thermodynamics. I know I've talked about this before, but the last time that we really discussed it, it had very informal language. So we usually have 3 and then some with the 0th law there. But kind of going through these things in order. The 0th law is essentially just the transitive property as it's true for temperature, right? And this seems like a very intuitive thing. Of course, if object A and object B are the same temperature, and object B and object C are the same temperature, then A and C better be the same temperature, right? It seems like an intuitive point, and it kind of is, but if you've taken any sort of math class with proofs, you know that transitive property is not always necessarily a true thing. So establishing that it's true for thermodynamics is an important step, right? Even if it feels intuitive, even if it feels like it doesn't need to be said, it's an important step to say it, to make sure that we've got it in case we need it in any proofs that we do, which we won't do in this class, but for all the physicists that are determining thermodynamics, it's an important step. So the first law is one that we have seen since 191, right? As we were looking at this before, we said, okay, energy cannot possibly be created or destroyed, only transformed. Every single time we talked about energy lost or anything like that, really that just means that energy is going into some other form that's not accessible to us anymore, right? In the form of like heat or sound from friction, right? That was just energy that we considered no longer accessible to our system. But it was still there, right? The second law, that was new for this course. This is really the definition of entropy. Heat flows from hot to cold naturally, right? The universe tries to become more homogeneous as time goes on, and entropy always increases. Those are just kind of parts of thermodynamics. You might see local circumstances where that goes, against the grain, but as a whole, entropy always increases. And then the third law is actually kind of our definition of what absolute zero really means, right? And I want to talk about this a little bit, and that's why it's highlighted here. We know absolute zero is 0 degrees, or 0 Kelvin. There's no degrees in Kelvin. Absolute zero, 0 Kelvin is the coldest you could possibly ever be. It is where our scale for temperature should start. But it's not really somewhere that we can ever get to. But how we actually define that is that entropy is constant. And I want to talk about what that means. Entropy, if we're looking at this on a microscopic scale at least, is essentially the number of different orientations of a group of particles, right? If we're thinking about that microscopic definition, it's basically saying the lowest entropy is when there are the least number of possible ways that I can arrange all of these particles. Highest entropy is when they're very evenly mixed, right? So when I'm looking at a realistic system, all of those particles are buzzing around in every which way, right? If I have a gas, it's not that any of those atoms are ever in a still position. They're always constantly buzzing around, which means, technically speaking, that the entropy is always kind of buzzing around a single point, right? It's kind of going back and forth constantly, all of these different motions. What if we were to stop that motion entirely, though? If we were to stop the motion entirely, all of the particles would be completely stationary. Entropy would now be a constant value. There's no more fluctuations in that value. It is now constant. And that's how we define absolute zero. It's when all motion has ceased. The momentum of any one particle is zero. Now, we might remember from some of our stuff like the uncertainty principle that actually localizing an atom down to a single point is not really something in the realm of possibility. But it does give us essentially a milestone, a marker of where our temperature value starts. And then it goes up from there. So it's an important definition to have, even if we're not going to necessarily use it that much in this course. Not zero. It's never zero. To have zero entropy means you have no particles. That's the only way to have zero entropy. Right? If we're thinking back to that definition, the entropy S is kb natural log of W, where W is the number of ways that you can have something. So even if you have one single particle, there's still one way to have that particle. And if there's one way to have that particle, entropy is not zero. So the only way to have zero entropy is to not have anything there in the first place. So let's talk about efficiency, right? Last time we saw that the first law of thermodynamics says, okay, efficiency, max out at 1. Can't be any higher than that. But there was somebody really clever that kind of determined that it's not actually that 100% is the highest efficiency that we can have because, well, there's more than one law of thermodynamics, right? We've got 3 and then 0, which kind of 4, but kind of in a middle spot, right? But Sadi Carnot actually understood that, okay, well, there is entropy to this engine, right? There's entropy associated with how we run this engine, and there is a limit to this efficiency that we can possibly get that is determined by that entropy limit. Not by the conservation of energy, but by entropy is really where the maximum efficiency of an engine can come from. So he figured out that the most efficient cycle you could possibly have, named after him, the Carnot cycle, is an engine that exclusively has isothermal and adiabatic transformations. That is how you get the most efficiency out of your engine. You only have those 2 types of transformations, right? At least for an ideal gas engine. And what that's really doing is you're trying to backtrack as little as possible, right? You're trying to only do extraneous work when you really, really need to get back to your initial position. You're trying to not expel any additional heat than what you actually need, but this is the way you do it. But it turns out that it doesn't really matter how many of these steps you have. If I have 50,000 transformations or 4, what it turns into, if I sum all of those up together, the efficiency of that engine always comes out to be one very clean equation, 1 minus Tc over Th. And Tc and Th are the temperatures of the cold and hot reservoirs, respectively. Right? And I kind of keep bringing this up that one spot's hot and one spot's cold, and we just kind of live with it like that. But it's been there for a reason, right? Th and Tc tell us about the maximum possible efficiency of this heat engine. It's talking about where is that input energy actually coming from? How hot is that? And where is that output energy going? How cold is that? And the larger that difference is between those 2 temperatures, the higher efficiency an engine is possible. But I want to specify here that when we're talking about these things, this old efficiency equation we have is still going to be true. It's not that the Carnot efficiency replaces the original efficiency of the engine, right? In fact, the Carnot efficiency is only telling us this is the maximum possible efficiency of an engine between these two temperatures. It's not that the engine is going to get that efficiency, but that's the upper limit of efficiencies that we might see. And there's an equivalent expression for heat pumps and refrigerators as well, right? But we're going to focus mostly on the heat engines here. So keep that in mind. We're looking at the difference between Carnot efficiency is the maximum possible efficiency, but regular eta, regular efficiency, is just the actual efficiency of that engine. Strictly speaking, eta is always less than eta Carnot. So let's try it in a concept check. If a heat engine was a Carnot engine, if this was a Carnot engine that I see in this picture right here, and I realize that it's still, let me bump this up just a little bit more. There we go. Now we can see the 200C. Operating between 400C as the hot reservoir and 200C as the cold reservoir, what range of an efficiency would I expect to see? Take a minute, think about it. It should indeed be less than 0.5. I'm not going to fault you if you thought 0.5, because at a first glance, that's what makes sense. But it is very important to consider what is the only safe unit for temperature. It's always going to be Kelvin. You're never going to be in a bad spot if you use Kelvin, right? We said that the only time you can use Celsius if it's a delta T, but if you use Kelvin anyways, if you use Kelvin all the time, it's always a safe bet. So let's label it, right? Use Kelvin. And if we use Kelvin, then what we see is really 673 and 473. So our 1 minus Tc over Th, that's going to give us something less than 50%. Any questions on that? Okay. Well, let's try it on a problem then. Let's say you have now graduated from physics. You are working in a Swiss patent office. Somebody has proposed 3 new heat engine designs. You look over these 3, right? And you're looking at essentially the broad details of each of these 3. If you are doing your job properly, meaning you are actually making sure that these things work first, which of these 3, if any, deserve a real patent? But also, yes, the only time you could get 100% efficiency is either TH goes to infinity or TC goes to 0. One of those 2. So, as for this problem, though, go ahead and take a look at it. If we look at this problem, we're going to need to go through this in order, right? The first thing we need to do is figure out first, does it follow the first law of thermodynamics? And I look at engine A, 500 comes in, 300 and 200 come out, that works. For engine B, 500 comes in, 200 goes out, 200 goes out. That's out. That's not happening. And the last one, 300 comes in, 100 and 200 come out. That works. So now we have to look at the Carnot efficiency and figure out if it violates the second law of thermodynamics. So we're in luck because all of these are 600 to 300. So the Carnot efficiency, or the maximum efficiency that we could possibly see, is going to be 50%. Right? And I'm really getting that out. Let me go ahead and go through the steps on that. The equation that I use, 1 minus Tc over Th. So I have 1 minus 300 over 600, which we might recognize as 1/2, or my maximum possible efficiency is 0.5. So let's calculate the real efficiency of each of these engines. I recognize this is my work out, right? My 300 joules is my work out here. So I can say, okay, for engine A, then I am seeing 300 over 500. Oh no. Oh no, no, no. 60% efficiency? I don't think so. It should not ever be greater than the Carnot efficiency. That is impossible. So engine A is out. The last one that we have, right? 100 over 300, work out divided by QH, 33% efficiency. That works. As long as we are less than the Carnot engine, we do not violate the second law of thermodynamics, and we are safe. So, engine C works. So, as we're moving forward here, we're going to dive into some longer problems. If you saw some of the nonsense, if you were here early for this one, if you saw some of the nonsense towards the end of last lecture, there are some longer problems coming up here. So it might be helpful to have kind of a strategy of how we approach these problems, right? So this is what the author recommends. And there are some things that I might do a little bit different. I might organize it slightly differently, but I think I generally follow all the same steps. Step 1, every single time, please draw a picture. It's so helpful. It's so helpful to have a picture. I promise. I do it every time, and not just for my health, right? Well, I mean, it saves me a bunch of sanity, so I guess it is for my health, but draw a picture. Once you have that, it's kind of like what we did with the review problems last time. Start to take each step along the process and find all of those state variables. And you might be combining this with the drawing step, right? That's not a bad idea either. If you are finding those variables and then drawing the process, so you've got kind of a good graph. Sometimes I draw a dummy graph before I go in, right? Just to kind of get an idea of what the shape's going to kind of look like. And then I find the state variables, and then I draw a real graph that actually matches that. But that is typically going to be a very important step. Once you have that, then I like to organize this into a separate piece. I look at, okay, transformation 1, transformation 2, transformation 3, however many we have of these things. And for every single one of my transformations, I like to look at the thermal energy, the work, and the heat. I actually look at work instead of WS, right? I like my regular W a little bit better because it makes more sense to me. It's what we did in 18 and 19. It's the most intuitive to me. I will wait to convert that to WS at the very end of the process once I have all these values determined. But once we do that, right, once we've got everything that we need to know about the transformations that the gas makes, then we look at this as a heat engine, we find QH, we find QC, we find work out, and we go from there. So, before we dive into that though, one more concept check, right? See if you've been paying attention and how well your short-term memory is working. I have some heat engine drawn up right here, operating between 300 Kelvin and 600 Kelvin. What is the regular efficiency? Not the Carnot efficiency, but what is the regular efficiency of this engine? You might at first think, after we've been looking at this for a little while, you might at first think that, okay, well, I see 300 and 600, and just like before, Carnot efficiency between these two temperatures should indeed be 50%, right? We could write that out. That's not wrong. But that's not what we're asking for here. The real trick to remember is that what is the Carnot cycle made of? We go back a few slides. The Carnot cycle is created exclusively from isotherms and adiabats. Anything else sacrifices efficiency, right? Immediately. Any other process is not as efficient. There are waste, heat, or work that are done in any sort of other process. They have more backtracking than is necessary. And so, if we're looking at a process like this, these are clearly not adiabats or isotherms, right? While our Carnot efficiency is going to be 50%, by the fact that we are not following those types of processes, by the fact that we're doing isochoric and isobaric processes, we sacrifice some of that efficiency. The highest we can have is 50%, but we know we have to be lower than that. So we are looking at less than 50% efficiency in this engine. It will only be the same as the Carnot efficiency if you are actually going through a Carnot cycle. So only if it's made exclusively of isotherms and adiabats can it actually be matching the Carnot efficiency, because that is a Carnot engine at that point. It's more of an ideal scenario though, because a lot of engines, it's not very practical to have only those two types of transformations. It's kind of difficult. And one of the problems in the back of the book, I don't think it's one that I assigned, but one of the problems in the back of the book talks about some real transformations that a real engine would go through and why it's a little bit different. It's not quite the same. So the Carnot efficiency is really just acting as the upper limit. We can get close to that, and we can make better engines that get closer to that Carnot efficiency, but actually hitting that, short of creating a Carnot engine, is impossible. Which, you can try and create a Carnot engine, it's not always practical in the way that we like to run things. So, here's a bit of a longer problem, right? And it might be helpful to kind of follow some of these initial steps. So, let's imagine that we have some sort of heat engine, and we go through 3 different steps here. First, isothermally compress until we have half of the volume that we started with. Then, isobarically expand until we get back to our original volume. Finally, isochorically cool until we're back to our initial state. So there's 3 points on this graph, but I want you to go through all 3 of these, write this all out, draw a picture. Please, draw the picture. Then find the thermal efficiency. And this is going to be a little bit weird because we don't have any numbers. But if we remembered how we treated the review problems from last time and how I kind of made a point of solving out all of the state variables in terms of our initial points, this is a solvable problem. I'm not just doing this for fun, right? This is a solvable problem. Okay, so I would like to draw this one out together, right? Just to make sure we're on the same page with this. Still got a little bit of time to keep working on this thing, but just make sure that our drawings look similar. So, if I was to draw all of this out, looking at whiteboard 21.5, PV diagram between these two. So we say that we start at some point, and I know where this is going to go, so I'm kind of drawing this with a little bit of foresight as to how this thing is going to go. So keep that in mind. But the first thing that we've got is we are going to compress to half of our initial volume, so 1/2 V1, and we're doing this isothermally. And if we're doing an isothermal transformation, that means P1V1 is equal to P2V2. That means if the volume is halved, the pressure is doubled. So 2 times P1 will end up right there. And this is what I mean when I say that we can really kind of like draw this at the same time that we're finding out the state variables. Sometimes that's helpful. It depends. If it's a really long process or something else like that, maybe it's not as practical to do that. But there's my first kind of rough picture. Here's state 1, state 2. And then we are going to isobarically expand back to our initial volume. So we're going to come straight across like that to point 3 here. So we're going to go there. And then finally, an isochoric back down to our initial. Right, and I'll draw little arrows to help me out here. So make sure your picture looks like this one. Right? It'll be very helpful to make sure that stuff's going to be wrong if it's not looking something like this. So, anyways, take another few minutes, see how far you can get into this thing, and then we'll take a look at it together. All right, so let's start to take a look at this one. And this, you might not be done with this problem or anything else, and that's totally okay, right? These are certainly longer problems. There are many, many steps to these problems. There's a lot of solving to be done. When I say that it kind of wraps up everything that we've learned so far into one problem, I really mean that, right? We're using things that we've seen from, well, at least 18, 19, and then this most recent chapter. 20 kind of is its own separate thing a little bit since it's talking about the microscopic view than anything else, but these are going to be longer problems. So if you're still working on this and everything else, go ahead and just kind of keep carrying on with what you're doing right now, but look up every now and then and make sure that our answers relate kind of close together, right? They should look similar. So what I'm going to do first off is I'm just going to kind of establish in each of my three states that I'm in, what state variables do I have? So in state 1, P1, V1, T1. State 2. Now, and I want to put these all in terms of, right, just all of these initial state variables. So I'm going to say, okay, well, I've definitely got the same temperature because this is supposed to be an isotherm. And that means that I am at 2P1 now, and I'm also at 1/2 V1, but I'm at the same T1 as I was before. And finally, in state 3, I'm still at my same 2P1. I'm back to my original V1. But if I'm also looking at this, then I can say, okay, well, I'm at a constant pressure. But if I remember from those transformations that we had from before, right? V2 over T2 is equal to V3 over T3. Basically what this means, that if the volume doubles, so does the temperature. Right? So that's exactly what we should see here. This is the only time we're not at T1, but we are at 2 times T1. Whoops, let me do that in black. And then we go back to our initial state. So, now that we've got all three states laid out, let's start to look at these individual transformations. So, I'm going to take first 1 to 2. And in 1 to 2, sometimes I like to write it out at the top here just to make sure that I know if it's a special process or something like that. It's an isothermal transformation, and that first off means that delta E thermal is going to be equal to 0. That makes life a little bit easier. So let's highlight that in red. That's one of the 3 values that we need to find for this. The next thing that we can do is we can solve out for what the work is supposed to be. So I'll say, okay, well, work is negative nRT1 natural log of, well, 1/2 V1, V final, over V initial. Which really means that this is nR negative nRT1 natural log of 1/2. So here's our first thing. We don't know what T1 is, right? And we certainly didn't know it up here either. It's some value. We also don't know the number of moles. We're not solving this thing anytime soon. We're not putting in exact numbers for any of these anytime soon. But in the meantime, because this is pretty much as far as we can go, let's just take it as is. And let's see where we can go with this. So here's one value that I've got, and I'm also, while I'm here, and let's highlight that, right? We got that. Now let's look at QH, or not QH, sorry, jumping way ahead of myself here. We look at Q, and we can say, okay, well, Q, that's just the positive of work, right? Or rather, the positive of this expression, but it's the negative of work. Since delta E thermal is going to be 0, Q is equal to negative W. That means that Q is equal to nRT1 natural log of 1/2. And I'm going to take this one step farther, actually. I wouldn't necessarily always do this, and I didn't do it up here because I didn't think it was super important at the time. But for Q, remember that at the very end, we're going to have to figure out which of these are positive and which of these are negative. And at first, this might look like a positive value. There's no negative sign out front. But remember, natural logs are maybe a little bit deceiving at first. A natural log of 1/2 is actually going to be, and let me make sure that I'm getting this right so I'm not messing anything up myself, so I'm not deceived on this, negative 0.693. So when I plug this in, this is going to be negative 0.693 times nRT1. Right? So be mindful of that. This Q is actually a negative value. But that's our third one that we're looking for. So we've got all three for that one. Let's go on to 2 to 3. For this one, we are looking at an isobaric case. So we know that delta E thermal goes as NCV delta T. Yee. Okay. Well, there's a few different things in here now, isn't there? I don't know the number of moles in, but that's okay. Do I know what CV is? Well, if we actually go back to the slide here, we are told that we're using a diatomic gas. And as long as we're doing a diatomic gas, then we know, I'll write it over here in this corner. CV is supposed to be 5/2 R. CP is supposed to be 7/2 R. So we do have those values at least. And then delta T. Okay. Well, I'm going back and forth between the third state and the second state. So let's write that out. So let's plug in some of the things that we've got so far. Times 5/2 R. T3 is just 2 times T1. T2 is just T1. When we put these all together, this is the, in terms of the same set of variables, we can actually reduce a lot of this stuff down. So this is going to turn into, in the very end, 5/2 in R T1. Nice. Okay, that's good to have. Next, we'll do work, and I'll say, okay, well, I know that this is an isobaric process, which means this is really just a big old rectangle, right? So it's a negative. I am at 2 times P1. And the change of volume, I'm going from 2V1 from 1/2 V1, which means that I end up with negative P1 V1. Oh no. So if we were solving a bunch of things out for N and T1, that seemed reasonable, right? The work up here had N and T1. This down here had N and T1. Then we saw N and T1. And we kind of got the idea that, okay, well, if everything's like this, if everything's in terms of N and T1, then maybe I can solve this out, right? Maybe some nice stuff is going to cancel out at the end. But now I've got 2 brand new variables. I've got a lot less confidence in that answer now. But let's not forget Chapter 18, coming back to haunt us all over again, right? Because we still have the ideal gas law. The ideal gas law is still a true statement, and that says that PV is equal to nRT. So P1V1 should be equal to nRT1. And we're back in those variables that we like to work with. The day is saved, we can go on. Right? But before we do that, let's find Q. Q, because it's a special process, is going to be NCP delta T. It's the same delta T as before, and we've already know what CP is supposed to look like, so this is going to be 7/2 in RT1. So we've got all 3 values for this state, and then finally, we're going to look from 3 to 1, and this is the home stretch. Isochoric means that delta E thermal is NCV delta T. Here, delta T is a negative T1, right? Keep that in mind. We are going to T1. We are coming from 2 times T1. So this is going to turn into a negative 5/2 in RT1. Work, 0. Nice. Finally, heat, Well, it's the same thing, right? Work is 0. Change of E thermal is going to be equal to Q. So there we are. Wow. That's a mess. Right? There's a lot of different stuff to work with there. But that's okay, right? Because now our job is to essentially piece through all of this stuff. We have an expression for delta E thermal for all of these, and that's not something that we actually need to know for our engine. And if you're actually solving problems like this, if you're trying to go fast, I recommend actually skipping E thermal, unless you really need to have it. There are some times where you do need to have it. If it's not a special process, if it's some weird diagonal line or something else like that, you will need to know what delta E thermal is supposed to be. But in a case like this, I'm just going to use it essentially as a check to make sure that all of my values match, right? Because we said before that if we are doing a complete cycle, we're coming back to our initial position. If we sum up all of those changes, it should come up to be 0. We should come up to our original energy that we started with. Positive 5/2 in RT1, negative 5/2 in RT1. It works. So we're on the right track. Now what we're going to need to do is we're going to need to sum up all of our works. We need to find workout. We need to find QH, and we can find QC while we're at it too. So let's start with work because that's the most intuitive. All 3 of these I have found not WS, but regular W, right? Our old W. So what I'm going to need to do now is I'm going to need to put a negative sign in the outside if I want to find workout. Workout is the sum. Ooh, that's a really ugly looking W, isn't it? Workout is the sum of all of WS. All of WS is the negative of regular work. So let me skip that middleman. Let me put a negative sign here, and then I'm going to say, okay, sum up every single work. Which means, if I look at my first step, that's negative nRT1. Natural log 1/2. And I look over to the next one, minus nRT1 plus 0. All 3 of my steps. I can simplify this down a little bit. Remember that natural log of 1/2 is negative 0.693. So what this really turns into is nRT1 times 1 minus 0.693. Right? So good so far? Turns out to be 0.307. And we're kind of holding on to that nRT1, but that's okay. We'll get rid of it very soon, I promise. So let's go ahead and highlight that in a light blue. There's our final kind of value here that we've got for the whole heat engine. Now I'm going to do QH. And remember that QH is the sum of every single time Q is positive. So, step 1, that's a negative. That's not it. Step 2, that's positive. Step 3, that's negative. So QH is actually just going to be 7/2 nRT1. That's it. That's enough to find the efficiency right there. But I might as well find QC while I'm at it just to beat the dead horse a little bit more. For some reason, my color didn't change. QC, every single time Q is less than 0, sum all that up and then take the absolute value. So I've got my negative on the other side. So this is going to be 0.693 nRT1 plus 5/2 nRT1. Right? 2.5 plus 0.693. I'm not going to bother simplifying that. Right? That's what we have for QC. So we're looking for the final efficiency of this thing. We're going to take workout. We're going to take QH. We're going to plug that stuff in together. nRT1, they cancel out. Everything works out in the end. And what we find at the very end is actually kind of a pitiful efficiency. But it matches exactly the efficiency we saw the other day. Kind of a funny coincidence, which is 8.77%. If you're answering in Canvas, it should be as a decimal. So that's messy. But it's a fantastic problem. It takes everything that you have learned so far and it combines most of it into one problem altogether with a lot of algebra. And every single time that I have recommended that you solve symbolically, well, now you really need to. There's not another option. So I hope you've been practicing, because it really is a necessity at this point. So we still have one part of this problem, though, that we haven't actually done, right? Even though we've done most of the work here, the last thing that we need to do is calculate the Carnot efficiency. And don't worry, this is just taking between the hottest and the coldest temperatures. So we found that the coldest temperature we were at was T1. And the hottest temperature we were at was 2 times T1. Which means that our efficiency, our Carnot efficiency, the most we could have possibly gotten would have been 50%. So, second law of thermodynamics is happy. All of the problem solving, making sure that delta E thermal summed up all together is 0. That still works. All of our stuff is good. This should be our final set of answers. So I know these are longer problems, right? But they are fantastic problems to work on. I really highly do recommend these. For practice and everything else, this is kind of the proof that you have covered all of this stuff. You've seen it before. You know how to deal with all of it. But there are a lot of little places that stuff can go wrong. So be careful on that. So let's talk about Stirling engines, because these are fun little engines. Unfortunately, I'm very upset. I have one of these. It's a mug top Stirling engine. I've got a YouTube video linked here that's a fantastic little one as well. Stirling engines are super cool. They don't have any internal combustion or anything else like that. They're very versatile because they only operate between a temperature difference. If you put some sort of temperature gradient around a Stirling engine, it runs. And it's much more useful for things that need to be done constantly, where work needs to be constantly applied, like a pump or something like that. It's not so great in other places where you need sudden energy, but it's got some really cool uses and everything else. But the cycle for a Stirling engine looks just like this, right? It's just 2 isochorics and 2 isothermals. So, we also have, I would highly recommend checking this out, in Dr. Alexander's lecture. If you go right to the, where is it? The 21-minute mark or so. And I'll pull this up as he kind of runs through this thing. I'm going to mute my own volume on here so I can kind of hear myself think. But this is, I think, a little bit of a nicer version than the one that I've got. But they are super fun. It's a waste of $40, but man, it's a really fun waste. But what he's doing here is he's taking, so he's got a Stirling engine, and he's got a tank here that's got a bunch of boiling or almost boiling water in it, right? You can see it steaming up there. He's going to scoop some of that in and just set this Stirling engine on top of it. And what that's going to do, the 2 plates, where the temperature difference actually is between the top plate, as you can kind of see it there, the top circular plate right there, that is at the temperature of the room, so around 20 degrees Celsius or so. The bottom plate is going to be right around, probably a little bit below 100 degrees Celsius for that boiling water, right? And it doesn't cover it completely, so there's a little bit of loss there, but kind of take it as it is. So it takes a little bit, it's got to get heated up, it's got to establish what that temperature is supposed to be, and then you need to give it a little bit of a push to get it started. You can actually see the compression, the expansion happening in the tiny little piston up here and the whole thing down here at the bottom. And as it gets up to temperature the rest of the way, it's going to spin faster and faster and faster. But it's just a really cool thing that you can see. They're super cool things. It's a really, really fun desktop toy. But as you'll see, it starts to go faster and faster. Let's skip ahead by just a little bit here. See when it's really Maybe a little bit more. There we go. It's starting to pick up speed. And you can see this entire time that it is spinning in one direction. Right? It will not spin the other way. I can't spin it the other way. It's going to, from our perspective, it really wants to spin clockwise, and it's going to continue doing so. You can't get it to spin the other way because that would be reversing the process, and it just doesn't work. However, if we jump ahead a little bit more, and now it's really kind of spinning. If we jump ahead a little bit more, you can see for a little while he has just placed this thing on a bunch of ice water now instead. But it's still kind of warm from the boiling water, so it takes a second to cool down. But let's watch it cool down for a little bit, and now we can see, okay, well now it's started to hit that 0 degrees. But the cool thing about this is that it still operates just on any temperature difference. So it doesn't matter that the cold reservoir is now on the bottom, the hot reservoir is on top. All that it does, you can see, now it wants to spin counterclockwise. It starts spinning in the reverse direction because the temperature gradient has flipped. So it's a super cool thing, and he describes it in a lot more detail here. He kind of walks step by step what he's doing and everything else. He's got another Stirling engine that he shows, a slightly different variation on it, right at the 21-minute mark. I do highly recommend going and looking at that thing. It is a super cool engine. It's a lot of fun to play with. But anyways, naturally, I don't know if you could tell that we were going in this way. Let's look at one. Let's imagine, what would the efficiency be? How would you actually write out an expression for this efficiency? And this is going to be kind of a nasty problem. I gotta be honest. There's some parts that are a little bit easier than the last one that we did, but the final expression does not come out as cleanly. So what I want you to do is find an efficiency for the Stirling engine based off of T1, T4, V1, V2. Those are the only 4 variables you need at the very end. And then what we can do, and I should have written this one as well. Once you have an expression for that, find what the efficiency actually would be. Let's assume, for example, that V2 is 2 times V1. And that's just something that depends on the design of the Stirling engine. How good is that compression ratio? Like that, it depends on the design of the Stirling engine itself. The mug top one, though, is probably about a 2 times compression or so. But really, I'm much more interested in this top portion, right? If you can find that expression at the very end, that's what I'm really looking for. All right, so let's start to take a look at this one. And again, if this is a really long one and everything else, and it's acted really tough, that's okay. This is a much longer problem than a lot of the other ones that we've seen before, right? So keep that in mind. But anyways, we've got 4 different processes that we're going to need to consider, but luckily it's essentially 2 sets of 2. Right, is really what we're looking at here. So let's go ahead and find some space here. I'm going to start, I know there's a picture here already, but I'm just going to draw a picture anyways. Right, that's just what I do. A perfectly straight line, and then a not so straight line. I don't know if you guys can actually see that with your resolution, but on mine it's there. So we say, okay, we start at some point up here. We go through an isothermal expansion, we go, should be straight down. And then we go through another isotherm, and that actually kind of lines up, not so bad. Point, 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 and then this point right here. Right, something like that. I know this doesn't look fantastic, but it's a graph for conceptualizing the problem more than anything else. So I'm going to call this point 1, call this point 2, call this point 3, call this point 4. Okay. So if I'm describing my states now, this one's going to be a little bit more complicated. See, we're going to run into an issue because state 1, say we are at some initial pressure, some initial volume, some initial temperature, and then the number of moles is constant still. Fantastic, no big deal. Whoops. State. Oh shoot, that never works like I want it to. That should just say state, that should say state 1. State 2. How does the pressure transform? I don't know. Because one of the problems that I run into is I don't really know how the volume transforms. I know it's the same temperature, so it's the same T1 as before. But again, looking at this thing, let's say the way that we're dealing with this, when I'm saying V2 is equal to 2 times V1, do not take that as something that we're plugging in right now. That is something that we plug in for this step down here. I want to find this first in terms of T1, T4, V1, V2. So I don't know what V2 is. And that's okay, I think. Let's solve it and try and find out, right? Let's see what happens if we leave P2 and V2 as is. Let's see what happens. Let's see if we actually end up needing them. So I go to state 3 and I say, okay, again, good luck with the pressure, I guess. I don't know what it is. Whoops, let me write that a little bit better. P3, whatever it is, but I stay at the same volume, and now I'm at T4, right? Keep in mind, T4 and T3 are the same temperature. State 4, we're going to say, okay, well, now we're at some P4, whatever that is. We're back to our initial volume, but we are still at T4. Okay. Let's see what we can do with this, right? Let's see how far this gets us. Maybe this is enough. That's always a possibility. So let's look at this transformation by transformation. 1 to 2. I know that there's no temperature change, right? This is an isothermal process, so delta E thermal is 0. Nice. Work is an expression that I have. So this is a negative nRT1 natural log of V2, because that's V final, over V1. Okay. Again, I don't really know how they relate. All I do know, one thing I do know is that V2 is greater than V1, right? And that's actually going to be an important point. We will need that point. Okay, but that's all I got for that one. I can't plug in anything else with that. So we go into Q and we say, okay, well, Q is just the opposite of that. It's positive in RT1, natural log of V2 over V1. And I can't do anything else with this. I have to leave that exactly as is. Okay, well, so be it. We keep going, 2 to 3. Now, I'm in an isochoric process, delta E thermal, but I kind of said this before. I don't care that much what E thermal is. It doesn't actually contribute to any part of the engine. Really, it's there as an additional step for us right now. Now, keep in mind, there are circumstances that you will need to use this. If I had some sort of crazy diagonal line or something like that, right? If my PV process had something that looked like that, right? Then we definitely need to know what E thermal is. We need to use that because there's no other way to find Q. You could find work, but you can't find Q without it being some sort of special process. So if it's any other ordinary process, you need to find delta E thermal, you need to find work. But in a case like this, because we never end up needing it, I don't care that much about it. So instead, I'm going to focus on work and Q. So work, because it's an isochoric process, 0. Nice. Heat is an expression, and it's an exact expression that I've already got. It is N CV delta T. Okay? Well, we're dealing with air, right? Air is primarily diatomic. So if it's mostly diatomic, we can safely say that CV is equal to 5/2 R. Whoops, whoa, drawn things a little bit too early. 5/2 R, CP is 7/2 R. So we come back up to here, and then we say, okay, delta T. Well, between 2 and 3, I am at T1, I am going to T4. So this is going to be N times 5/2 R T4 minus T1. Now, here's an important point. T4 is smaller than T1. T1's the hotter temperature, right? We start at T1, we go down to T4. So what that means is that this Q right here is actually a negative value. And we're going to need to know that when we come back to solving for QH. But we've got that for now. And again, we're trying to put this all into terms of the variables that we're after, right? T1, T4, V1, V2. 3 to 1? Not 3 to 1. We have an extra step, don't we? 3 to 4. We're in another isotherm. Delta E therms equal to 0. Work, still negative in RT4. Natural log, we are going to V1 from V2, so it's all flipped. Wouldn't it be nice if we could make this look like the others, though? It really would. So what I'm going to do is I'm going to pull a negative sign out of this, and because it's in a natural log, I can use a negative sign to flip this thing around. So this is going to turn into in RT4 natural log of V2 over V1, and that's just a property of natural logs. It's not a physics thing, it's a math thing. But that way it looks kind of like the others, right? It's natural log of V2 over V1, just so it matches and looks like everything else. Okay, and then we go into Q, and in the exact same way, now this is going to be a negative in RT4, natural log V2 over V1. And I know it seems kind of redundant, but making the natural log look similar on both sides is just, it's a useful thing, I promise. Well, we got that. Okay, and finally, 4 to 1, our very last step here. Again, delta E thermal, it's the exact same expression as before. It's not 0, but it's NCV delta T. We might notice here, though, that keep in mind, I didn't fill in the details with this delta T, right? But for 2 to 3, I'm going from T1 to T4. For 4 to 1, I'm going from T4 to T1. So these two delta E thermals are exactly equal and opposite, right? Which, if we wanted to prove the delta E thermal at the very end is all equal to 0, yes, we did. Fantastic. But anyways, keep going on. No work is being done, so that's nice and easy for us. Q, again, looks in the exact same way as before, but it's flipped. So now it's going to be an N 5/2 R T1 minus T4, which means it's a positive value. So we zoom out, we take a look at everything that we've got all at once here. Okay, I said V2 is greater than V1. So any place we see natural log of V2 over V1, that is a positive value, right? So there's no non-intuitive stuff going on here. But I can look at these things and I can say, okay, 1 to 2, that's a positive value. 2 to 3, that's going to be a negative because T1's greater than T4. For 3 to 4 here, I see a negative sign, and the natural log is still positive, so that's a negative. So 2 to 3 and 3 to 4, those are both part of QC. So let's write it. QC, QC. Here, part of QH. Part of QH. Excuse me. At the end of these things, my voice always starts to go. But anyways, so by looking at which heats are positive, which heats are negatives, we get essentially which ones are going to be our QHs, or what's going to be contributing to QH, what's going to be contributing to QC. So we might as well start there, actually, because this would be enough to solve out for our efficiency as is. So QH would be in R T1, natural log of V2 over V1, plus this thing over here, which is much nastier. Let me pull out the 5/2 to the front. In R T1 minus T4. Yikes, not as pretty. But that's okay. Then we go over to QC, and we can do the exact same thing, but we know it's going to be the exact same thing, right? We know it's going to be some value. We sum up these two things together, take an absolute value because it's going to be a positive thing, right? When we're looking at the whole system, we know what it's going to be. We don't need it for the efficiency. I like to work with work out instead. So just as before, work out is going to be take the work of every single one of these, throw a negative sign in front of all of it. So that'll look first like this. negative nRT1, natural log of V2 over V1. And then we've got the exact same thing over here on the other side. Plus nRT4, natural log of V2 over V1. Right? And this is exactly why I said at the very beginning that we should try and make that natural log look the same on both sides, because now let's move that negative sign into the inside and let's distribute these things. Let's pull out what's the same between all these variables. And what we get then is nR natural log of V2 over V1 times T1 minus T4. Beautiful. That's simplified nice and easy. Right? That's a lot prettier than what we just saw. So now we have an expression for workout. We have an expression for QH. If we want to find the efficiency, let's bring those two together. So we're going to get this very nasty thing. And is there a cleaner way to do that? I'm just going to leave this as is. nRT1 natural log V2 over V1 plus 5 halves nR T1 minus T4. This is unfortunately not going to come out to be a very pretty answer. I've got bad news if you're expecting this to simplify very, very nicely. All of that is under my nR natural log of V2 over V1, T1 minus T4. So some of the things that I can do to simplify this, though, I can first cross out the nR from every term. That's gone. And then I can try and... It looks a little bit cleaner if I divide everything by natural log V2 over V1, honestly. So if I do that, this turns into T1 plus 5 T1 minus T4 divided by 2 natural log of V2 over V1. I know that looks kind of nasty, but it like when you put it in terms of the whole fraction as a whole, it looks a little bit cleaner. T1 minus T4. And that's our final simplified answer for the efficiency of the Stirling engine. I know it doesn't look super pretty, but kind of prove the point that we can settle it with just these 4 variables. Now, we might want to compare the Carnot engine. If we compare it like that, say the Carnot efficiency is going to be 1 minus TC over TH, and we said, okay, well, TC is T4 over TH is T1. And let's go ahead and try and group this to make it look kind of similar here. What we could do is we can combine these two into essentially T1 minus T4 divided by T1. Would you look at that? So if we compare it over here, we can see that for any time V2 is going to be greater than V1, which is always, we established that as our main big sticking point, we can see that essentially you either have to increase that temperature difference a lot to increase the efficiency, which we know, of course, or you make that compression ratio, V2 over V1, very, very large, and this term will start to get smaller and smaller and smaller, and we approach the Carnot efficiency because of that. So it's a cool way to kind of reduce that. If you can really increase that compression ratio, you can create a really, really efficient Stirling engine. So the very last thing we can do is actually plug in the values that we've got for this thing. So I said, let's say a mug top Stirling engine, because it's not a very great engine. The compression ratio is V2 is equal to 2 times V1. Let's do this all in a different color, actually. Let's do this in, let's do it in purple, just for fun. V2 is equal to 2 times V1. When we do something like that and we say the T1 is going to be equal to, this is the hot temperature, so this is 373 Kelvin. T4 is just going to be 293 Kelvin, right? Some very hot coffee to a standard room. We can start plugging all this stuff in, right? So natural log, that will turn into natural log of 2. I'm going to go ahead and plug this stuff in on the spot, actually. So natural log of 2 times 2 And this is 5. The difference between those two is 80 degrees. When I plug all of this stuff in, I end up finding that for the mug top Stirling engine, I've actually got a pretty decent efficiency of 12.09%. That's not too hateful. Right? Versus the Carnot efficiency of this thing would be, let's see here. Considering the Carnot efficiency is going to be 21.45%. That's not bad. Right? It certainly beats the engine that we saw earlier, where we were only getting 8% versus the Carnot 50%. But that's how it goes. So they're cool little engines, right? I think they're really, really neat. We'll close out 21-2 with that. So this is the final lecture before Exam 1. All the material up until this point is what Exam 1 will end up covering. Next lecture is going to be exclusively review. So within that, the best use of our time on that one, it might not necessarily be the same questions or anything else throughout the entire thing. So what I'm going to be doing is I'm going to be bringing some problems to do during that review. But I think a better use of our time is for you to bring questions that you're having some trouble with, and I can answer them then. Because realistically, I might be pulling questions that you guys might already be masters at, right? I'm not entirely sure. But if you bring me questions that you're struggling with, then we know for certain that we are answering questions that I can be helping with, and it's not just redoing stuff that you guys might already know. But to fill in the dead space, if there is any, and hopefully there's not, but if there is, I'll have some questions myself that we can all work on. And I'll just kind of talk through how I'm doing a lot of these things. So, that's the end of that.